Ladies and gentlemen, thank you very much for attending our session on ICIS 2022. Today I will present to you my paper named A Lightweight Image Colorization Models based on GeoNet Architecture. I completed this work with Dr. Phan Duy Hung and we come from FPT University, Vietnam. The presentation today is divided into 4 parts. The first part is to introduce to the problem as well as the related work of other authors and our main contribution to this topic. And the second part is for methodology, where we present the proposed model as well as the loss function. And the third part is for implementation and evaluation, where we will show how we prepare for experiment and evaluation. And the last session of the presentation is for conclusion and future works. Firstly, I would like to introduce to the problem. Image colorization is to assign a color to each pixel of a grayscale image. For example, I have a grayscale image and I would like to assign a color to each pixel to make it more vivid, more colorful, just like the right image here. This is a very difficult problem because 2 of the 3 channels of the ground truth image was lost. The objective is to find the most plausible color to assign to each pixel instead of finding the lost original color. The main application of image colorization is to colorize legacy image or video. There are various approaches for image colorization. Before the era of deep learning, human intervention is usually required for colorization, for example, color scribble or reference image. However, during the era of deep learning, many authors had introduced their fully automatic method to colorize images. The common approach in deep learning is to predict schematic A/B channel from given lineage channel by propose a CNN. After predicting the schematic A/B channel, it will merge into the lineage channel and generate a colorful image. For the related work, as I mentioned above, many authors had introduced their method to colorize images. Before the era of deep learning, Levin in 2004 introduced a color scribble image colorization method. Chabias 2008, Liu 2008, and Gafter 2012 introduced their methods of image colorization using reference images. For deep learning approach, Zhang, Izuka, Larson in 2016, Royal 2017, Zhang 2017, Zhao and Victoria 2020 have introduced their methods for semantic colorization. Other authors like Royal 2017, Despont 2017, Messar 2018, Zhao 2020, and Wu 2021 focus on diversity of color in generated images. For performance improvement, Zhu in 2019, Kalian 2019 and Su 2020 have tried to improve their methods for better performance. However, almost all of them have introduced a quite large model for predicting the A/B channels. For example, Zhang in 2016 and Larson in 2016 introduced a model which had 128 MB and 589 MB of parameters. They are very large and it would be very difficult to deploy the model on mobile device. Heavy model requires a lot of time to colorize an image and much more time for long video or movies. This motivated us to propose a lightweight model for semantic colorization which had equivalent performance to the state-of-the-art colorization methods. Our proposed model is lightweight and fully automatic. It predicts A/B channel from the given lineage channel like other methods. It is also assumed to colorize images of any resolution. And finally, it is self-supervised learning, where a part of the raw input is used as a sort of supervision. This figure shows the proposed architecture in our model. It is a simplified version of the GeoNet. And like other architecture in image colorization, it had a contracting path and an expanding path. Skip connections are added to the model to keep the detailed information that may be lost during the downsampling process. Mask pooling is used for downsampling and upconvolutional layers are used for upsampling. After predicting the AB channels, we merge it into the lineage L channel and generate the colorful image in lab's color space. Images of any resolution are resized to 256 by 256 before processing and will be restored to the original resolution after prediction. Mean square errors loss function is used to evaluate the predicted mark. To show how lightweight our model is, we compare to the model of Larson and Zhang in 2016. As you can see in the table number 1, Zhang model has 1 and 29 megabyte parameter, while Larson has 588 megabyte parameter. Our Pro model has only 55 megabyte parameters. In general, the model of Zhang is twice larger and Larson is 10 times larger than Pro models. The cubic in the presentation shows how relatively lightweight our model is. The next section of the presentation is for implementation and evaluation. To prepare for experiment, we use two different datasets. The first one is Pascal VOC 2012. We use this for evaluation and quantitative comparison to other methods because it is a commonly used dataset for image colorization. The second dataset is BLAZY 205. We use this for qualitative comparison to state-of-the-art methods, as well as showing how well the model works on such large datasets. We build our model based on TensorFlow framework, and the hardware used for training is NVIDIA GeForce GTX 1650 CPU. For the training process, we use midi-batch training, and the midi-batch size is 16. ADAM optimization is adopted. On BLAZY 205 dataset, a single epoch takes about 7,500 seconds to be completed, and the validation lot reached a lower limit after about 20 hours, equivalent to 140,000 iterations. For quantitative comparison, we use two metrics. The first is RM at E, and the second is PSNR. While RM at E is a standard metric, the PSNR is a commonly used metric for image reconstruction start. We also report the runtime of predicting a single image in a non-GPU device. As you can see in the table number 2, regarding to RM at E, Larson in 2016 reached the best performance, while Zhang in 2017 reached the best performance in PSNR. However, for the runtime, our method is the fastest one, with only 113 seconds for predicting a single image in a non-GPU device. It is 3 times faster than Zhang in 2016 and 10 times faster than Zhang in 2017 methods. For qualitative comparison, we train and evaluate on BLAZY 205 dataset. As you can see in the picture, our predicted images are compared to the ground truth. For example, in the image of the sea and the sky, our generated image is quite close to the ground truth. However, in the other image of nature, our generated image have less green than the ground truth. I call it the gray effect of our generated image. However, in general, images generated by our methods are quite close to the ground truth. We also compare our generated image to other methods. As you can see in the picture, the first column is a grayscale image. The second is a prediction of Zhang 2016. The third is Zhang 2017, and the fourth is our predicted image. And the last column is the ground truth. And as you can see, there is much more green in the image generated by Zhang method than our method, and even than the ground truth. And we call it the green effect of Zhang's method. The green effect makes the image generated by Zhang method is more vivid and more colorful. However, sometimes they look unreal, like the first row image of the railway. Image of Zhang method have much more green than our methods and even the ground truth. The railway is even green. However, in fact, the railway is not green in the ground truth, as you can see. The green effect also causes the method of Zhang will do better on the image of nature, while our method will do better on the image of less green things like car, horse, lake, and railway, for example. So in summary, we have introduced to you my works, which propose a colorization model which is very lightweight, which had only 55 megabytes of parameter. It is also very fast comparing to other methods, with only 113 milliseconds to predict an image in a non-GPU device. It generates images as close to ground truth as other state-of-the-art methods do, like Yang in 2016 and 2017. In the future, we will customize a loss function and apply it into our model to resolve the gray effect and the desaturated problem. We also develop an application for video colorizations based on this proposed model. And finally, the simplified U-Net architecture in this model can be viewed as a convolutional part of other complicated colorization model. That's all about my work I would like to introduce to you today. Thank you very much for your attention.